Okay, so this video is about implicit differentiation. So just so you know, implicit differentiation allows us to find the derivative of functions that are not written explicitly as a function of a single variable. So what I mean is this. If I graph x squared plus y squared equals 25, this is not a function. It's actually a circle. If you graph it, it's a circle with a radius of 5 and a center at 0, 0. So if you actually graph this, the radius go out to 5 in all directions from the origin, 0, 0, which is the center. So this would be the graph for it. R equals 5. So that would be the graph for it. And basically, it's not a function because it doesn't pass the vertical line test. Like if I took a vertical line, and I place it on this graph here, it would touch it in 2 places. So because it touches in 2 places, it's not a function. Because the function has to pass the vertical line test. You have to put a vertical line on it. It has to touch it in 1 place. Now, there are some places I can place a vertical line that touches in one place. That would be like right here. But every place else, it would fail the vertical line test. So because of that, we can still find the derivative of it if using implicit differentiation. So today we're going to talk about implicit differentiation, where we find the derivatives of equations like this. All right, so let's go. I need to erase the screen. Okay, this is our first example. It says find the derivative of the equation y squared equals x. All right, so I already kind of know this equation is not a function because y is getting squared. If you graph this equation, it would look something like this. It would be a sideways parabola that's centered at the origin. And that's not a function because it does not pass the vertical line test. It fails the vertical line test. But we still can find a derivative. And this is how we do it. If I want to find the derivative of y squared equals x, you basically take the derivative of the left side with respect to x, so derivative of y squared, and take the derivative of the right side with respect to x. All right, so the derivative of y squared, using the powers rule, it would be 2y to the first y prime. All right, whenever we take the derivative with respect to x, and we have x and y here, and we take the derivative of both, we have to keep in mind that with the y section of the graph, we should call that the derivative of the function times the derivative of the letter, and that deals with using the chain rule. So essentially, the derivative of any function would be use the powers rule as always the derivative of the inner function. In this case, it's y. This is always times y prime or x prime. But I think we talked about before. Typically, if I take the derivative of x, it's just 1, because if I thought about that, it's really the derivative of x, which is 1, times x prime. So the derivative of any function would be the derivative of that one using powers rule times the derivative of the part there. Now, the derivative of x is still 1, so it's just 1 times 1, so it gives you back to 1. Anyway, long story short, you don't have to do this x prime stuff when you're trying the derivative of x. Only you have to consider that when you find the derivative of y. So when I take the derivative of y, it is 2y times y prime, but y prime may not be 1. All right, and again, so the equation is 2y times y prime equals 1. If I want to finish solving this, I want to isolate y prime. Our goal is to figure out the derivative. So I would divide both sides by 2y. So, that being said, the derivative would be y prime equals 1 divided by 2y. That's the derivative of it. Now, if you actually know what y is for the original equation, you can't replace it. Like, we could have taken this equation and solved it for y, and we could replace it there. And that's another way of actually finding the derivative. So, if we wanted to, we could have, I'm going to pause the video. I'm going to erase all this, and we're going to find this answer a different way. So, remember to get everything that you can write down. I'm actually write this a different way. But before I erase it, I want to make sure this is clear. I can write this a different way. If I showed you this equation, y squared equals to x, and you want to solve that equation for y, you probably square root both sides. And you get y equals to positive negative square root of x. So y has two different parts to it, positive square root of x and a negative square root of x. So if I want to replace y, I could rewrite this as y prime equals to 1 over 2 square root of x, or 1 over 2 or negative 2 square root of x. So y prime could be both of those because you have plus or minus sign in that function. So, but anyway, so this would be the derivative of it without having a y, only having y prime and x. All right, so keep that in mind. I will get that copy. Now I'm about to erase the screen and talk about finding that derivative a different way. Now let's reconsider the same equation. We'll give you y squared equals to x. If I want to find the derivative there, you might think, well, can I isolate y first? So you get y equals positive or negative square root of x. So y could be square root of x, or y could be negative square root of x. And if I want to find the derivative, you probably think, well, this is a rational exponent, so it's x to the 1/2. And we've done this enough times to know that this is going to be y prime equals to 1/2 x to the negative 1/2, or 1/2 over the square root of x. And the other one would be y equals negative x to the positive 1/2. And if you took the derivative, it would be y prime equals to negative 1/2 x to the negative 1/2, or negative 1 over 2 square root of x. All right, so that's two ways we solve this. One would be a traditional way that we'll probably begin solving that for x by isolating y first and then taking its derivative. And the other way would be taking the derivative of each term using implicit differentiation, because it wasn't really a function. For example, if you graph this function as it is, it would be y equals positive square root of x and y equals negative square root of x. So positive square root of x starts at 0, 0, looks like that. Negative square root of x starts at 0, 0, is the reverse of it. So basically it should look something like a sideways parabola. It's not really a corner there, it's more parabolic. So anyway, so it's basically sideways parabola. If you thought about what that function would be as a graph. So anyway, so that's how you find derivative using implicit differentiation. Some equations get a bit more complicated than this one though. So let's look at some of those. Alright, so this example says find the slope of the circle here. The one we began with talking about at the point 3, negative 4. So I like to get a visual of what I'm trying to do before I begin. So I want to think about this as a graph first. This circle has a radius of 5. This is at 5. This is at 5. This is at negative 5. And negative 5. Anyway, so we want to find the coordinate 3, negative 4. So that's down in this quadrant. This will be coordinate 3, negative 4. And to find the slope there, it would be the slope of some tangent line that looks something like that. So I know my slope ought to be positive when it's all said and done. And I know I'll have a negative y-intercept and so forth. But that's what I'm looking for. I'm looking for the slope at this point. So what I would do is, I would find the derivative of that equation. So we begin with this equation which says x squared plus y squared equals 25. And again, this is not a function, so we'll use implicit differentiation to find the derivative of it. So it'll be the derivative with respect to x in the first term plus the derivative with respect to x in the second term, and the derivative of the right side of the equation. So you got to take the derivative of all parts on both sides of the equation. And the first term derivative should be just 2x. The second term derivative should be 2y times y prime. And the derivative of 25 should be 0. So from there, our goal is isolate y prime. So let me subtract 2x from both sides. X y prime equals negative 2x, and then y prime must be negative 2x over positive 2x. Oh, that's a typo. That should be an x. That should be a y. So this should be a y. This should be a y. So that reduces to be negative x over y. All right, so this is really useful to know that y prime equals negative x over y. So, since y prime equals negative x over y, we got a coordinate that's 3, negative 4. This is x, and this is y. So y prime has to be negative 3 over negative 4, or 3/4. So the slope at that particular point must be positive 3/4. So we found it. We found the slope at that place. Am I right? Slope. That's remind myself. That's what I just found. All right, so that's what you do in that problem. One more. Oh, I'm about to clear the screen, so if you need it, I'll copy it. All right, so it says find the equation for the tangent line to the ellipse written here at the point. So you could graph this ellipse and find the point or whatever. I would. You can go to Desmos, or you can think about how to rewrite this in the form of an ellipse and graph it. But it should look essentially like this. It's going to be some ellipse that looks like this. Something like this. And the coordinate negative 1, 2 is somewhere around there. So the tangent line would be something like this. We went through the process of actually graphing all that. But anyway, let's talk about finding the derivative of this. So one derivative of the first term, second term, and all the terms. So it should wind up being 2x is the first derivative, subtract. This is product rule. So essentially going to be the first times the derivative of the second plus the second times the derivative of the first, which is what? Plus, derivative of this is 2y, y prime, and derivative of 7 is 0. Now, we'll clean this up a little bit. So it's going to be 2x subtract xy prime, subtract y plus 2y, y prime equals 0. To solve this for y prime, you need to isolate the y primes so you can cancel out a y prime, factor out a y prime. So move everything else away. So I'm subtracting 2x from both sides, move it away. I'm going to add the y to both sides, so move it away. Leaving you with negative x y prime plus 2y, y prime equals to negative 2x plus y. Now, since both of those have a common factor of y prime, I can factor out a y prime and call this y prime times negative x plus 2y equals to negative 2x plus y. And our final step, we divide by this parentheses, so y prime's alone. So I'm going to use some space above to do that. So y prime equals to negative 2x plus y divided by negative x plus 2y. So that's the slope at any point. They gave us a very specific point to find the slope at, or actually the equation of the tangent line at. So if you want to find the equation of the tangent line at this place, you want to replace all the x's and y's with negative 1 and 2, respectively. So y prime at negative 1, 2 is negative 2 times negative 1. I need more space in this, so right beneath. So it's negative 2 times negative 1 plus 2 over negative 1 plus 2 times 2. So that value of y prime should equal to, this is 4, denominator is 5. So y prime equals 4 over 5. So I know the slope at that place. Well, better yet, y prime at 1, 2. So y prime at negative 1, 2 is 4 over 5. And my final step is writing the equation of the tangent line. I need to erase the screen, so if you could copy it and then come back to us. I'm about to pause the screen and clear it. All right, so remember, we found our slope to be 4/5, and our point was negative 1, 2. We can plug that all into the formula. You should have this. So y subtract 2 equals 4/5 x plus 4/5. And you add 2 to both sides. So y equals 4/5 x plus 2.8. That would be the equation for the tangent line That's all I have. Good luck.